Hey, what up, y'all? Welcome back to the next class. Actually, we're 2 classes behind because I've been having some problems with uploading these things. Anyhow, just wanted to let you know, midterm here upon us. Um, all you really have to do is complete what's online since everything's moved online, and if you do that, you're good. Check this out. This is one of the things I love about astronomy, of deep space, and this is why I throw this in here. This is one of the NASA Space Telescope's first images that shows a distant supernova split into 4 different images. This is what's called gravitational lensing, and one of the importances of this is showing that the images are showing that there is unseen matter, sometimes called dark matter, that is actually causing such a huge gravitational distortion that light is bending around it. This phenomenon, gravitational lensing, was it's very similar to what Albert Einstein predicted we'd see if gravitational distortion was able to bend light. It would magnify and distort an image of something behind the gravitational force. And this image, where you see the 4 points, is actually called an Einstein cross. So the elliptical galaxy in the foreground and its galaxy cluster is 5 billion light years away from Earth, and the supernova behind it is 9.3 billion light years away. And this image is from November 11th, 2014. So this image, this is the galactic center with what's called the arches and quintuplet star clusters. And what we're seeing here is intense wind and radiation forces from the massive stars in the quintuplet have excavated the dense gas clouds surrounding the cluster. And look at the arrows. It's kind of where we're pointing at. And what we're seeing is that the dust disk around these smaller stars living in these clusters are exposed to these same forces, and the dust itself is being blown away. It doesn't last for very long. And this image is dated from March 10th, 2015. So what's interesting about this image in particular is, what do we know about the formation of our solar system from reading through the textbook? We believe that our solar system was formed from a solar nebula, and everything kind of contracted to the central region of higher gravity, right? Until nuclear fusion, just kind of summarizing the process, occurred in the sun. And when that happened, all of the planetary formation in our solar system basically stopped. The interstellar wind and radiation from the sun pushed any remaining gas and dust away from us, right? And that's a very easy summary. So this image, what's unique about it is that in March of 2015, they released this image, and we've detected about 20 rotating dust and gas disks in each of these clusters that host exceptionally large and hot stars. The existence of these disks in the presence of the UV radiation field, their massive neighbors, is surprising, because astronomers have been wondering, based on our model of solar system formation, shouldn't all these large hot stars be blowing away all this gas and dust? It shouldn't be there as long as it is under the conditions. And some of these stars are considered to be 100 times more massive than our sun. So what does that mean for the theories that, remember, a theory is a hypothesis which withstands testing. What does that mean for our solar system formation theories? These are some important topics. We're going to briefly, as you can see, there's like only 11 slides in this. And I'm going to make this short, and then we're going to move on to discussing more of the same on the next lecture post. So the word power, it's already defined here. I'm just going to add a smidge more. Perhaps the easiest measurement to make of a star is its apparent brightness. I'm purposely being careful about my choices of words. When I say apparent brightness, I mean how bright the star appears to the visual observer here on the Earth. The luminosity of a star, on the other hand, is the amount of light it emits from its surface. The difference between luminosity and apparent brightness depends on distance. Another way to look at these quantities is that the luminosity is an intrinsic, almost like intrinsic being like a property of, of the star, which means that everyone who has some means of measuring the luminosity of a star should find the same value. So, however, apparent brightness is not an intrinsic, inborn property of the star. It depends on your location. So everyone will measure a different apparent brightness for the same star if they are all at different distances from that star. For another analogy, which everyone's familiar with, is think of the headlights of a car. When the car is far away, even if its high beams are on, the lights will not appear too bright. However, when the car passes you within 10 feet, its lights may appear blindingly bright. To think of this another way, given two light sources with the same luminosity, the closer light source will appear brighter. However, not all light bulbs are the same luminosity. If you put an automobile headlight 10 feet away and a flashlight 10 feet away, the flashlight will appear fainter because its luminosity is smaller. Stars have a wide range of apparent brightness measured here on Earth. The variation in their brightness is caused by both variations in their luminosity and variations in their distance. An intrinsically faint nearby star can appear to be just as bright to us on Earth as an intrinsically luminous distant star. There is a mathematical relationship that relates these quantities, apparent brightness, luminosity, and distance for all light sources, including stars. This would be, look on the bottom right, the inverse square law for light, and it is discussed in your textbook. Definitely worth looking at. Okay, I just have to say first off here, there's a common theme of these learned, wise people. They always look very saintly and wise, like they're going to bestow some power unto you. Look here, I will grant you the power of determining stellar brightness. So astronomers still today use a system of measuring stellar brightness called the magnitude system that was introduced by the ancient Greek scientist Hipparchus. In the magnitude system, Hipparchus grouped the brightest stars and called them first magnitude. Slightly fainter stars were second magnitude, and the faintest stars the eye could see were listed as sixth magnitude. You notice the magnitude system seems backwards, like the brighter a star is, the smaller its magnitude. Our eyes can detect a factor of 100 difference in brightness among stars, so a first magnitude star is about 100 times brighter than a sixth magnitude star. We have preserved this relationship in the modern magnitude scale. So for every 5 magnitudes of difference in the brightness of two objects, the objects differ by a factor of 100 in apparent brightness. So if object A is 10 magnitudes fainter than object B, it basically is a huge difference in brightness. If object A is 15 magnitudes fainter than object B, it can be 1,000,000 times fainter. And that's a very summarized version. But remember that objects' apparent brightness depends on its distance from us. So the magnitude of a star depends on distance. Given that all, if we were to say that all stars were the same, were producing the same luminosity, the closer the star is to us, the brighter its magnitude would be. That is the apparent magnitude of a star as we see it on the Earth. There is another magnitude scale that we use in astronomy, and that is absolute magnitude, different than visual magnitude. And this absolute magnitude is based on how a star would look if all stars were, or how bright a star would appear to be if all stars were at a common distance of 10 parsecs. And this absolute magnitude scale is really a great equalizer for us, because now we get to take out the distance. Everything's in an equal distance, and now we're just looking at how much luminosity is actually being put off by these objects. And what that means for us as observers is, well, if a star is farther than 10 parsecs, but it's very bright and we're getting very few photons of light from that distance, well, then at 10 parsecs, it's going to be extremely bright. But if there's a star that's really close and it's much dimmer and putting off low luminosity but appears bright because it's so close, well, at 10 parsecs, it's going to look very dim. And that means that the brighter object that's further away is going to be lower on the magnitude scale, meaning that it will appear brighter, and the dimmer object that's closer and gets moved to 10 parsecs away is going to appear much dimmer and will be higher on the magnitude scale. And that might sound confusing, but you just have to remember that the magnitude scale appears backwards. The lower the number, the brighter; the higher the number, the dimmer. And this is what I'm talking about right here. And if you look at this slide, we have improved beyond just basic telescopes that we look through. Now we've thrown in things like CCD cameras that allow us to view things that are much fainter. And we've also been able to see things with negative magnitudes. Look at Sirius's apparent magnitude is negative 1.47. Now, of course, keep in mind that when we're talking about these magnitude scales, the ancient, Hipparchus scale didn't go negative. It was 1 through 6, and there was no negative 1.47. All right, let's cut to the bottom of this slide and talk about Alpha Centauri, the Alpha Centauri system. If we were going to find aliens, this would be the first place we should look because it's the closest. Proxima Centauri is the closest star to our own solar system and is the third star in the Alpha Centauri star system, also known as Alpha Centauri C, with a distance of 4.2 light years. One of the things we're getting into is spectral types, and that is a spectral type M5.5, Roman numeral 5, lowercase c. If you are a fan of the old television show Lost in Space, or the new one, this is the place they became lost. So one of the things here, and going back to ancient astronomy and putting a nail in the coffin of the geocentric model, parallax. This word defines the historical hurdle that kept the Ptolemaic model in power for way longer than it should have. Remember that we had Aristotle and his idea that the Earth was surrounded by spheres and the stars were in the fixed sphere that didn't change. Part of this was that the stars were all equidistant from the Earth. This thought was carried forward into the Renaissance period, with many astronomers knowing and desperately wishing to show that stars were at a different distance from the Earth. Copernicus, Galileo, Brahe, whose name I always pronounce improperly, Kepler, all had to live out their lives knowing that they were correct in the assertion that the sun was the center of the solar system, and if they just had the proper equipment, they could prove the Aristotelian foundation of the Ptolemaic model was incorrect. What did they lack? A better, bigger, more powerful telescope called a heliometer. So in the 1830s, there was this guy named Friedrich Bessel, and he had this telescope called a Fraunhofer heliometer, the same Fraunhofer who did work on the solar spectrum for, Fraunhofer lines. This heliometer telescope had micrometer screws that would take the main telescope mirror, what's called the object mirror, and it would move it. And that sounds like nothing, right? Well, this telescope had this amazing mirror that had been cut into two pieces, and you could take this mirror and make images move. The original purpose of this telescope was to measure the angular size of the sun. First, if you were Bessel, you would know a ton of math, right? Second, you would know the angular size of the field of view you were seeing through this telescope. Remember, field of view, the more you magnify, the smaller the field of view. Well, this guy, he had to know it, right? So what he did was to look at the different stellar objects and play with the mirrors so that he could measure the distances between the two mirrors. He did this periodically, and most especially at two distinct times of the year, 6 months apart. Why? Because when we are looking at parallax, we are looking for changes in position, the positioning between two objects. We're looking to see if the object in front moves with relation to the object in back, right? That's what parallax is. That's what we're looking for, to show that stars are moving, or that there's or that there is an apparent motion in space. And that also shows us that objects are not on a fixed sphere all at equal distance. That there's objects closer and there's objects further out. And that sounds really elementary, but that's had to be proven to show that the universe is much bigger than we think and we're not the center of it. And we do this naturally with our eyes. You can play that game where you put your finger out at arm's length and you close one eye and open the other, and then close the other and open the other. And you'll see that the objects behind your finger appear to shift, right? It's built into our binocular vision. But when we look far away towards mountains on the horizon, we couldn't tell what was near or far on the mountain without some magnification. And this is the same for annual parallax. Annual parallax was the first stop in discovering and proving the parallactic measurements of stars, and Friedrich Bessel knew, based upon the elliptical orbit model that Kepler had developed, that the Earth would have to be at opposite points of the orbital ellipse about the Sun if he took similar measurements or stellar measurements 6 months apart. So there was this star called 61 Cygni that was barely visible to the naked eye and was considered to have a high radial velocity, or in other words, it was thought to have moved faster across the night sky than other stars, but it was unmeasured. If 61 Cygni moved so fast across the sky, it surely would have to be closer than the stars that move slowly across the sky, right? Remember, we're talking in relative terms. We're talking about distant stars that don't appear to move to us. We only see distance of about 1 degree every 75 years or so. These stars don't really appear to move relative to one another if you were to stare at them for a night. So he took these measurements and found that 61 Cygni carved out a relatively small ellipse in the sky relative to other stars, and this is called annual parallax because it's due to the fact that the Earth is at two different points in space 6 months apart. With this observation, parallax was demonstrated. This is 1830s, right? What do we know about 61 Cygni and what Bessel did see? 61 Cygni is a 6.4 visual magnitude star in the constellation of Cygnus, the Swan, and what Bessel recorded was a change in position of 1/3 of a second of arc. Remember, arc is measurement on a curve or on a sphere. This isn't something you can observe without the magnification of a telescope. You absolutely have to have a telescope. And when we talk about parallax, this is what we're talking about. We're talking about, on the bottom it says, a parsec is the distance at which an object 1 AU across has the size of 1 arcsecond. 1 parsec is equal to 3.26 light years or 206,265 AUs. And while I really didn't do this slide any justice, I'm just throwing it out there when we talk about parallax and parallax angle and an equation to measure this. We're going to get more into this over the duration of the rest of the semester, but I'm throwing this out there. And I'm sorry if that sounds confusing. So, just for the fun of it, Hipparchus satellite. Out there measuring parallax to a high degree of precision. And I'm just leaving this slide up so you guys can read it. But done with this one. And I'm going to keep going on because these chapters kind of flow together. So stay tuned.